Hi, this is Brendan, and I will be discussing the current progress of the project. To start, we will look at the construction of the pin transfer robot. As you can see, we have constructed the base and the overall structure of the robot using both V-slot linear rails and C-beam linear rails. When constructing the base gantry design of the robot, we had to tap and thread the rails to be able to include mounting hardware to secure the rails together. With the structure of the robot completed, we then added the linear actuators. Currently, we only have one X-axis linear actuator mounted onto the robot because we are waiting on mounting hardware. After we get those parts, we will be able to mount the remaining two X-axis linear actuators. We were also able to mount two C-beam linear actuators onto one another. This can be seen on the top part of the robot, where a shorter C-beam linear actuator is mounted on to a gantry cart that is attached to a longer C-beam linear actuator. One of the more important parts of our progress on this project is the ability to control multiple motors at the same time. As you can see in the video, we are able to move the motors together such that they finish their movements at the same time, or we can independently move the motors. We were initially having some problems with the motor drivers sent to us from the manufacturer. They had sent us two different versions of the same motor driver. Because of this, we fell into some trouble when we were trying to set up the drivers with the motors, thinking that they would be wired the same way despite being different models. However, after realizing that the drivers needed to be wired differently, we were able to resolve this issue, and we can now operate the motors by interfacing them with the motor drivers. Another important point of progress in this project is the LCD display. At this point, we are able to ask the user for information by displaying text and other graphics on the screen, and we are also able to gather input from the user via the touch screen on the LCD display. As shown in the video, the user is able to enter information via the touch screen, and the microcontroller is able to capture that data, which is then shown in the serial output of the device. We have had some progress on the application as well. Currently, we can receive and send basic Bluetooth packets to and from the application in the Bluetooth module that we are using. We have also constructed the emergency stop button. However, we have not wired the terminals of the button yet.
As we were building our project and testing it, it occurred to us that there were a few things that we could improve. One of the things we wanted to change was the size of our X-axis NEMA 17 stepper motors. You can actually buy some NEMA 17s with smaller bodies, which would reduce the congestion along the rails holding the motors. Additionally, upon placing the 96 wall plates on top of the gantry carts we had, it was clear that they were much too small, and we needed something larger in the total area to hold them. The 96 wall plates are about 127.8 millimeters long and 85.6 millimeters wide, which is much larger than the 65mm square surface area that our gantry carts currently support. In light of that, we plan on changing them to the universal V-slot gantry carts that have a length of 127mm and a width of 88mm, almost exactly matching the dimensions of the wall plates 1:1. When we realized that wiring and programming our NEMA 17 and 23 stepper motors was simple enough, it was time to consider whether it was worth replacing the stepper drivers with ones that were much smaller, since they each occupy a lot of space. Finding an enclosure that holds all of them along with the power supply, which in itself is already huge, will be all the more difficult. We plan on comparing our drivers with other smaller motor driver designs to see if they could fit well for our project. We may even design a MOSFET circuit to do the motor driving for us if it comes to that, but only time will tell. For the development of the app, we plan on switching from the HCO5 module to the HM10. The two HCO5 modules we were testing had a lot of inconsistencies in their programming. The first HCO5 module we were using would refuse to change its baud rate, and the other would accept the change only to revert its settings once connected back to the circuit. The HM10 we were testing turned out much better and much simpler to use, not to mention it supports BLE and has a range of 100 meters in open air compared to the measly 10 meters that the HCO5 had. The increase in range means that the researcher can still get updates on the progress of the liquid handling robot while being further away. Hopefully, once we're done with all of the last minute changes that we need and we find that everything that we tested works in accordance with our technical specifications, we will be moving all of our circuitry away from the breadboards and into the PCB once we have everything soldered.
Hi, this is Chris Clifford. I'm going to talk about the storyline of our final demo for senior design. So to start, I'm going to talk about the technical specifications that we decided we were going to meet at the beginning of senior design and how we're going to demonstrate that we've met those technical specifications by the end of our project. So the first technical specification that we are going to demonstrate that we met is that the cycle time for our pin transfer process is less than 2 minutes in total. So this would be from it picking up the first input plate, transferring the chemicals into the cell solution, and then washing the pin tool and going back to its starting position. The second technical specification is the dimensions of the robot. We're going to make sure that the robot is less than 21 inches tall, 46 inches long, and 18 inches deep. At the very least, if our robot exceeds these dimensions, we're going to show that the linear actuators don't actually traverse outside of these dimensions, and that if we had the time, we could chop the aluminum extrusions to make this robot fit within the dimensions that we've put in the technical specifications. The third technical specification that we're going to demonstrate that we've met is that we can power the robot using a 120 volt wall outlet, which is the only source of power inside of a biosafety cabinet. So this is either a pass or fail metric. The fourth technical specification is that the robot weighs less than 50 pounds. This is important so that the operator can pick up and place the robot into the biosafety cabinet. So we'll measure this and demonstrate this using a scale. The fifth technical specification would be to make sure that we can sanitize the robot, and we'll do this by providing a list of all the materials that we used in the robot and that they are compatible with alcohol, 70% ethanol. Then we will demonstrate that our GUI for the LCD works and that we can use the mobile app that we developed that communicates over Bluetooth with the robot. We'll demonstrate that that works as well. And we'll follow up with a demonstration on how to operate the robot and how to properly use the mobile app. And then to close off our final demo, we'll show an entire full cycle of the robot where it completes a fake pin transfer process using dyes in water to demonstrate that it's transferring a small amount of chemicals.
For this part, I'll be talking about the remaining challenges we have to deal with. The first issue is that we still need to order and mount limit switches for the linear actuators. The limit switches will allow us to accurately give directions to run the motors so that the gantry carts are in the correct places at the correct times. We also need more gantry carts per actuator. We'll need to have 3 more carts for the wash step actuator, 2 more for the cell plate actuator, and 2 more for the chemical plate actuator. And we'll chain all of the carts on each respective actuator together with more of the belting. Currently, our cables are just out, so we need to cover or hide them somehow. We also need to mount our power supply onto our machine. We know where we want to mount it, but not exactly how that will be done. So we'll need to figure out how that'll be done, and then we'll need to get the parts to mount the power supply. We have our emergency stop button, but it's not hooked up to anything yet, so we just need to hook that up. We have our PCB and all of the parts for it. We just haven't soldered any of the parts on yet. Once everything has been soldered on, the PCB will also need to be tested to make sure that everything is working correctly. We need to mount the LCD onto the machine. We have an idea of where we want to mount it, and we just need the parts to do it, and for the code to be finished before we mount it. Currently, the machine shakes a little when the actuators are running, and this is something we'd like to avoid. So to do that, we're going to add rubber feet onto the bottom of the machine. We just have not bought the rubber feet or any other parts that are needed to put the feet on yet. We'd also like to increase the mobility of the machine by adding handles onto it. The only issue with our current design for this is that it would require 2 people to carry rather than the preferred 1. We also don't have any parts for this yet. We need a way to constrain the plates to the gantry carts. We currently have an idea of adding on 4 little corners to the ends of the carts, although we're not sure if we want to buy these corners or 3D print them. We still need to mount the pin tool to the Z-axis actuator. We're currently in the process of ordering the plate that we're going to use to mount the pin tool. So once we get that plate in, we can mount the pin tool. And then the pretty much final part is that once everything has been put together, we need to test the speeds on all of the actuators so that we can find safe movement speeds for the well plates so liquids do not come out of them while they're being moved.